morning and welcome to ENE 496. What I'd like to do today is talk about the photon lifetime of a cavity, the Q of a cavity, and then I would like to move on to a discussion of resonators, the stability of resonators, and some of the algebra associated with optical resonators. So let's just first talk with review of what we have seen previously in terms of the what is the finesse of a cavity. We've seen that F, the finesse of cavity in the presence of losses, can be written as pi R1 R2 to the power 1/4 e to the minus alpha s L over 2, where alpha s is the background absorption in the cavity. The whole thing is divided by 1 minus square root of R1 R2 e to the minus alpha s L. Okay, so this is the expression that I previously gave you for the finesse of a cavity, and this takes into account the fact that the mirrors might be of different reflectivities, and it takes into account the fact that there is some background absorption in the cavity. If there is no background absorption, then e to the minus alpha SL divided by 2 is equal to 1, and this is also equal to 1, and we get back the previous expression for the finesse in the case when you don't have any loss. We have also seen that this expression can be written as pi exponential minus alpha r L over 2 divided by 1 minus exponential minus alpha r L. And in that expression, alpha r is known as the distributed loss of the cavity. So where alpha r is defined as the background absorption coefficient plus the distributed loss of the mirror, which is 1 over 2L ln of 1 over R1 R2, like this. So here you see that the background loss is given by this, and now what we have done is mathematically, this is correct, is we have distributed the loss of the mirror over the whole cavity, okay, by doing it like this mathematically. Now you can substitute this into this expression and find out that this is equal to that expression above. Okay, so that's a justification, but here I just want to stress that this term is known as the distributed loss for the mirror, and you can think of it as alpha mirrors. Okay, you can also write this as 1 over 2L ln over R1 plus 1 over 2L ln over ln of 1 over R2. So in this way, distributed the loss of each of the mirror over the whole cavity. Okay. Now, if we take R square, if we define R square, small r square here, as, if you define it as R1 R2 exponential minus 2 alpha s L, okay, so if you define r square like this, which is the same thing as exponential minus 2 alpha r L where now we use the our definition of distributed overall distributed loss, alpha R. Now, so if we define this quantity R square, here R square, we have mentioned this, is after one round trip, RT, one round trip. The intensity is a factor R square of the incident intensity, Okay? So now, so if you take R square, which is after one round trip, the intensity is a factor R square of the incident intensity. So this is what we mean by R square. So here you see that after, if you go over one round trip like this, then you have here R1, R2. So if you go over one round trip, if you start from here, then you get the intensity is reduced because of R2, and then you go twice, it's a round trip, so it's twice the distance between the two mirrors, so you get exponential minus 2 alpha SL, and then when you hit this mirror again, then the intensity is reduced by R2. So R square is the intensity, is a factor by which the intensity is reduced after one round trip. So if you use that definition of R square, then the finesse can also be written as pi square root of small r divided by 1 minus r. Just by inspection, you just, if r squared is defined like this, then by inspection you can see that the finesse can be written like this in terms of the factor by which the intensity is reduced after one round trip. Okay? So there's different ways of writing the finesse. Now, so let me erase this now, so I can use the whiteboard again. What we're going to do is we're going to look what happened when in the case where alpha RL is much less than 1. So here, when the distributed loss, the overall distributed loss is much less than 1. Okay, so I will keep that expression here, and I will erase the rest because I need the space. Okay, I'm going to erase this, and let's see, for alpha RL, so for the distributed loss here, if we take it to be much smaller than 1, then we can write that the finesse is about equal to pi divided by alpha RL. And where is this coming from? What we have done is we've just done the Taylor expansion L exponential x, when x is small, is about equal to 1 plus x squared over 2 factorial, and we neglect these other terms here. So we just take exponential of x to be about equal to 1 plus x. So that's the approximation. And here in the numerator, we just have to make this exponential about equal to 1. So we get pi. In the denominator, you make the exponential as 1 minus alpha RL. And because of the minus sign here, the 1 cancel, and you just left with alpha RL in the denominator. Okay? So this is the approximate expression for the finesse in the case where the distributed loss is very small. Okay, so now I'm going to erase the rest here. like this. And then we're going to introduce the concept of photon lifetime. Photon lifetime. This is an important concept. It's a measure of how long the photon, live in the cavity, because the photon will bounce back and forth between the mirror, and finally the energy going to decay away, the energy of the cavity. Okay, so what we're going to do is we're going to use delta nu full width at half max, the expression we have gotten before, which is expressed in terms of the free spectral range, you remember that, divided by the finesse. Okay? Now, we're going to use the fact that the finesse is approximately given by this expression in the case where the distributed loss are small. So it means that the mirror reflectivity is high and the background absorption is low. Okay? So in that case, you can write that nu free spectral range divided by f. Nu free spectral range is always c over 2 and l, the l being the distance between the two mirrors. So c over 2 and l, and f we've seen is equal to pi over alpha r. Let me rewrite this. Pi divided by alpha r l. Okay? So that gives us an expression for the fluid half max of our resonance in the Fabry-Perot. And this can be written as C over N times alpha R divided by 2 pi. Okay? So that's the full width half max. Okay, now let's just look at the fractional energy loss for a round trip in the cavity. This is given by this fractional energy loss for a round trip is 1 minus r squared. Right, r is little r that we have introduced before. That's the fractional energy loss for a round trip, because r was the fraction of the incident intensity that was left after one round trip. So 1 minus r squared is the fractional energy loss for a round trip. And now if you take 1 minus r squared divided by 2l, then what we're going to get is the fractional energy loss per unit length. So the fractional energy loss, let's see, since I have a little bit short of space, I will just write this, the fractional energy loss per unit length, is just 1 over 1 minus r squared divided by 2l, because that 1 minus r squared was the fractional energy loss for a round trip. So per unit length you divide by the round trip, which is 2l. Okay? So what we get from this is 1 minus r squared is just given by use the definition of r squared, which is exponential minus 2 alpha rl. So you get 2 alpha rl divided by 2l here. Then the fractional energy loss per unit length is given just by alpha r. Okay? So that's the fractional energy loss per unit length is in fact equal to alpha r. Okay? Now you can write, so I'm going to erase this to make some room. Now we can write the fractional energy loss per unit time. Okay? And now this will be given by multiplying alpha r by c over n, the speed of light. So c over n times alpha r is the fractional energy loss per unit time, because the fractional energy loss per unit length is alpha r. So if you multiply by the velocity of light, then you're going to have the fractional energy loss per unit time, which is c over n times alpha r. Okay? So now we're going to, let's see, I'm going to make some room here. And then, so now I'm going to write the energy in the cavity decays according to the following equation. And the following equation says dE over E, so that's the fractional energy loss per unit of time. Here, if you divide by dt, is per unit of time. So this is the fractional energy loss per unit of time. And we've seen that the fractional energy loss per unit of time should be equal to c over n alpha r. So I can write this as minus c over n alpha r. It's a minus here because the energy is decaying inside the cavity. Okay? So now, so I can make some more room here. I want to keep that expression here for the full width half max I've written. So here, the solution of this equation, so you can put dt on that side, and we can do the integral, which is an easy equation, and what we have is the solution is just given by the initial energy e to the minus c over n alpha r t. That's the solution of this equation. Okay? Or this can be written simply as E0 e to the minus t over tau photon. You see that's a characteristic time here. This is how fast the energy in the cavity is going to decay. So here the photon lifetime, the way it's written, it means that tau p is equal to 1 over c divided by n times alpha r. Okay? Okay, so here this implies tau p is equal to 1 over c divided by n times alpha r. Okay, that's our photon lifetime here. Okay, so photon lifetime in the cavity is given by this expression. Okay, this is the way the energy decay inside the cavity. Okay, now on the other hand, if you remember your Fourier analysis class, if you have something that decays like this exponentially, then it means that in the frequency domain, this implied by doing the Fourier transform, okay, this implied that the width, full width half max here is given by 1 over 2 pi tau p. So the width in the frequency domain associated with this decay of the cavity, it means that you have the full width half max to be 1 over 2 pi tau p. So now, if you use that expression, you know, for the full width half max, 1 over 2 pi tau p, and then if you use the tau p given by this, what you get is 1 over 2 pi tau p, so you get in the numerator here c over n multiplied by alpha r. Okay, and then so this is what you get, 1 over 2 pi tau p using our definition of photon lifetime, and you see that these two expressions are completely compatible, and this is what you would expect. Okay, we get the same expression. So we found that the photon lifetime, if it is given by this leads to a broadening in the frequency domain. And previously we have seen that the broadening in the frequency domain was just given by this expression here, and we have complete agreement between these two expressions, as we should, of course. Okay, so now I will erase this, and I'd like to introduce the concept of the Q of the cavity. Okay, and I will relate this to the finesse of the cavity. So here we're trying to make a connection between the Q and the finesse of the cavity. Okay, so I will erase this to make some room. Okay, so the quality factor Q of the cavity. So Q, as we have seen before, and as you have seen in your electrical circuit class, Q is just given by 2 pi times the stored energy divided by energy loss per cycle. Okay, so that's the Q of the cavity. That's the way Q is defined. And so now C over N alpha R is the fractional energy loss per unit time. That's what we have seen. We have just seen per unit time. Okay, that's C over N times alpha R. Now C over N alpha R divided by nu zero. Nu zero being the frequency of the light. Okay, so it will give us the fractional energy loss in one cycle of the light. Okay, if you divide C divided by N alpha R, if you divide this by nu zero, then it will give you the fractional energy loss in one cycle. Because here we just multiply 1 over nu zero is just the period of one, of the electromagnetic wave. So this is one cycle. So that will tell you is the fractional energy loss in one cycle. Well, that's what we want here, is energy loss per cycle. So here we have the fractional energy loss. Now the energy loss per cycle is just given by the fractional energy loss per unit of time multiplied by the stored energy. The loss per cycle is C over N alpha R divided by nu zero multiplied by the stored energy in the cavity. Right? That would be the energy loss per cycle. Since we have the fractional energy loss per unit of time, if you multiply by the stored energy, that would be the energy loss per cycle. Okay, so this is this quantity. Now if you plug this in this expression, the stored energy will cancel, and what you're going to get is that Q is equal to 2 pi over C over N alpha R over nu zero. Okay, and this can be rewritten as nu zero, put it in the numerator, and you recognize this as delta nu full width half max, right? So this is the delta nu full width half max, the inverse of it. Okay, so therefore Q is equal to nu zero divided by delta nu full width half max. And this can be written in terms of photon lifetime. as we have just seen. So we can write this as 2 pi nu 0 tau photon. Okay, that's another way of writing the Q in terms of photon lifetime. And we know that delta nu full width F max is just given by nu free spectral range divided by F. So therefore, this can be written as nu 0 divided by nu free spectral range multiplied by the finesse. So here we express Q in terms of the finesse of the cavity. Okay? So Q is equal to this, but Q is also equal to this expression in terms of photon lifetime. So these are different equivalent expression. Okay? So that's good. Okay. So now what I'd like to do is discuss optical resonator with spherical mirrors. Okay? So you're gonna need this expression here for doing your homework, your upcoming homework. Okay? So let's move on to the optical resonator with spherical mirrors. Okay. So optical resonators with spherical mirrors. Spherical mirrors. Okay? Well, I just want to remind you what the electric field looked like what the electric field looked like for a Gaussian beam. Okay? So you get E for both LM, the X components, and how it varies with R. We get an expression that looks like this, W0 over W of Z. We had the Hermite polynomial, square root of 2x over W of Z. That's the other Hermite polynomial for the M mode, for the other axis. So square root of 2y W of Z multiplied by exponential minus x squared plus y squared over W of Z squared. Okay, and now we add the phase terms. So we have ik x squared plus y squared over 2rz. This is the off-axis phase expression. And now on the axis you get minus ikz and minus plus I L plus M plus 1 times eta. Okay? So this is the phase on axis. Okay? Where eta is equal to tangent minus 1 of Z over Z0. Okay, so here we know how to calculate the phase on axis for a Gaussian beam. Okay, so just remember this expression, and now I'd like to discuss optical resonator further, and what happened when you use two curved mirrors. So the basic idea is that you have a Gaussian beam that looks like this. You remember, it looks like this. And now we have these phase front like this, and they have some radius of curvature. And the same thing on that side. You get some radius of curvature. Now what happened is the basic idea of resonator is that we'd like to put a mirror with the radius of curvature matching the phase front of the Gaussian beam. So here, if we take two mirrors of different radius of curvature, but you match the phase front then you would see that Gaussian mode would still be a solution for that resonator. Okay. So the solution for the optical field inside the resonator are still those of the propagating Gaussian beam, if we do that. Okay, so having drawn this and having written this expression, now I have to make some room. I'm going to erase this. And so here, since the normal of the propagating beam here, since the mirror exactly match the phase front, the ray here will come normal to the mirrors, and they will retrace, will be refocused back to the to a beam ways, and then the beam will just keep on reflecting between the two mirrors. Okay? So we can form an optical resonator merely by inserting at point Z1 and Z2. This is Z1 and this is Z2. I'm sorry. Here the notation is Z2 and this is Z1. So Z2 and Z1. So if you put two curved mirror there, they could be a different radius of curvature. So an optical resonator can be created merely by inserting at point Z1 and Z2 two reflectors with radii of curvature that match those of the propagating spherical phase front at these points. Okay? So this is in word what I've said. So now we won't be using this right now, but I will just let you know for the future what we're going to say in a few lectures from now. Since the surface are normal to the direction of energy propagation, the reflected beam retraces itself. We said that. What we're going to learn is that if the round trip phase shift between the mirror is some multiple of 2 pi radian, so the round trip, if the phase of the round trip is some multiple of 2 pi radian, then we're going to have a self-reproducing stable field configuration. And this is the way we are going to calculate the resonant frequency of the resonator. But this we're going to do that in a few lectures down the road. Okay, so for now we don't need to know this, but I thought I should mention it at this point. Okay, so now we consider a cavity. So let's consider a cavity formed with two spherical mirrors, one with radius of curvature R1 and the other one with the radius of curvature R2. And these two mirrors are spaced by a distance L. Okay? Okay. So now what we can do is we write the expression for the radius or curvature of the phase front. R1 is equal to Z1 plus Z0 squared over Z1. That's our normal expression for the radius or curvature of the Gaussian beam. At position at Z1 here, and then at Z2, then the radius of curvature would be given by Z2 plus Z0 squared over Z2. Okay? So now, if you look more closely at each of these equations, what you get, if you multiply by Z1 here, you get Z1 R1 is equal to, you put this on the common denominator, so you get Z1 squared plus Z0 squared. Okay? Okay, So what you get is the equation quadratic. You see, this is a quadratic equation for Z1. You recognize the quadratic equation? I can just rewrite this as Z1 squared minus Z1 R1 minus Z0 squared is equal to 0. And now you recognize this as a quadratic equation. You can do the same thing for this here. You would have Z2 squared minus Z2 R2 minus Z0 squared is equal to 0. Okay? So now the solution of this quadratic equation are given. Since it is a quadratic equation, you can write that Z1 is equal to R1 over 2 plus or minus 1/2 R1 squared minus 4 Z0 squared. And the same thing, Z2, the solution is just given by R2 over 2 plus or minus 1/2 square root of R2 squared minus 4 Z0 squared. Okay? So these are the solution of the quadratic equation. It means that if you know R1 and R2 and you know Z0, or equivalently if you know W0, because Z0 and W0 are simply related, then you can find the position of Z1 and Z2 where you need to place the mirrors in order to perfectly match the Gaussian beam. Well, in practice, you don't have a Z0. What you're given is Z1 and Z2. I'm sorry. What you're given in practice is R1 and R2. You have two mirrors of different radius of curvature, and you want to put them at some separation. So L is equal to Z2 minus Z1. Okay? So L is equal to Z2 minus Z1. Okay? So now you're given R1, R2, and L, which is Z2 minus Z1. So you get three equations with three unknown, and you can find the position as a result of this equation. You can find Z1, Z2, and Z0. These are the three unknown. Okay? I just want to digress here a slight bit to stress one thing is if you look at the solution here for Z1 and Z2, you have two solutions, right, for Z1 and two solutions for Z2. And the reason for that is very simple, is that if you think of a Gaussian beam, this is where the beam waist is, like this. And then, so the plane, the face front is parallel. And then here the curvature, curvature increase. And then it decrease, when you go away. So first, you see, you go from a radius of curvature infinite. Here, your radius of curvature gets small to a minimum, and then it starts expanding again. So you see there are two positions of Z that have the same radius of curvature around the position where you find the minimum radius of curvature, or maximum radius of curvature, I should say. This is where you get maximum radius of curvature here. Okay, so that's why you get two solutions here for the same radius of curvature. Okay, so, and the same thing for the other mirrors. Here you would have, same type of situation. Okay, so that's why you get these multiple solutions. Okay, so we are interested again to see the case where we are given R1, R2, and the distance between the mirrors. Okay, and we'll see how it works. Okay. Okay, so we have this equation here, and we can solve these equations. The way we solve them is, for instance, Z2 here, we just replace it by L plus Z1. Z2 replaced by L plus Z1. And then we plug Z1 here, so you get L plus this expression is equal to this. Okay? So Z2 is equal to L plus Z1. Okay? And so you do L plus R1 over 2 plus or minus 1/2 square root of R1 square minus 4Z0 square. So L plus Z1, which is Z2, so this has to be equal to Z2, which is R2 over 2 plus or minus 1/2 R2 square minus 4Z0 square. Okay? So this is equal to this. Okay? So now these two expressions, we have two equations here, and we can extract the Z0. I mean, we don't have two equations. We have this is equal to this, and we can extract the value of Z0 from that equation. And if you do this, then you find, and this is left as an exercise, you find that Z0 squared is equal to the following expression. L multiplied by minus R1 minus L, R2 minus L, times R2 minus R1 minus L, divided by R2 minus R1 minus 2L squared. So this is the solution of this equation here. So you find that Z0 squared now is expressed in terms of R1, R2, and L. Okay? And since we know Z0 now, then we can find the position Z1 and Z2 where we need to put the mirrors. Okay? So that's good. Okay, Z0 squared. So now we're going to use that expression for Z0 squared, and we're going to apply it to the case of symmetrical mirror resonator. So let's look to the case of a symmetrical mirror resonator. Mirror resonator. Okay, symmetrical mirror resonator. So it's a special case of this situation. And what we mean by symmetrical mirror resonator is just that R2 is equal to minus R1 is equal to R. Okay, so the two mirrors are the same. They have the same radius of curvature. Okay, so in that case, if you plug this into that expression, then you're going to find out that Z0 squared is equal to L. If you do this, then you get R minus L, this term, because minus R1 is equal to R. Then the next term is R minus L. And this one is 2R minus L. Then divided by, here we get 2R minus 2L, so we factor the 2 out, so we get 4. And then we're left with R minus L squared. Okay? So that's what we get there. Now R minus L times R minus L is R minus L squared. Okay? So we find that Z0 squared in the case of the symmetrical mirror resonator is just given by L times 2R minus L divided by 4. Okay? That's Z0 squared for a spherical mirror resonator. Now, you know that W0 is simply related to Z0 via this expression here. Lambda 0 Z0 divided by pi n, the wavelength of the light in the material, which is lambda 0 over n, and then to the power 1/2. Now if you do this, then you get lambda 0 over pi n to the power 1/2 times z0 to the 1/2. Okay, here we have z0 square. So we have to do it to the 1/2. So you take L, you get this expression to the power 1/4. So you get L over 2 to the power 1/4, and then R minus L over 2 to the power 1/2. No, the power 1/4 also, I'm sorry. Okay, so we get this, and here we have we have taken the factor 2 in outside. We have factor out 2. Okay, so that's why we get R minus L over 2 here, and we get L over 2 to the power 1/4. Okay, this is for W0, and once you know W0, you can calculate W1 and 2, and I will erase this here, and we can write W1 or 2, which is the size of the beam on mirror 1 or mirror 2. It's just given by, we use the fact that W1 or 2 is equal to W0 times 1 plus Z1 or 2 divided by Z0 square to the power 1/2. Okay, that's our usual expression for W, the spot size. It varies as a position of distance, and then we substitute this into that expression here, and what we get is, using the value of W0 that we found, we get W0L divided by 2 pi n to the power 1/2 multiplied by 2R squared divided by L, R minus L over 2, the whole thing to the power 1/4. Okay? So this is using, here in this expression, we got this expression here by using Z1 is equal to minus L over 2, and Z2 is equal to L over 2 for a symmetrical resonator. For a symmetrical resonator, the beam waist has to be right in the middle of the cavity. Okay? So therefore Z1 is equal to minus L over 2, and Z2 is equal to L over 2. So if you put this in that expression, then you should be able to demonstrate that W12 is equal to this using our value of Z0 square for a symmetrical cavity. Okay, so you get this expression, and this can be rewritten, this is just rewriting here, lambda 0 L over 2 pi n to the power 1/2, and now this is 1 divided by 1/2 L over R multiplied by 2 minus L over R, the whole thing to the power 1/4. Okay, so we just rewritten this expression here in terms of L over R. So we took the R square, we put it in the denominator here, we get L over R, and then we get 1 over R, we factor out the R here, and then we get to this expression. Okay, so this is the expression for the spot size on mirror 1 and 2. It's given in the case of a symmetrical mirror cavity. Now, since we have W1 and 2, it's given by this. I'm going to erase here again to make some space. I'm going to erase this here. And what we can do is take dW of 1 or 2, either one, as a function of a radius, and you want to find out when this is a minimum. So minimum of W12. So minimum spot size on the mirror is obtained when this is equal to 0. And when you do this, and I will let you do this derivative, what you should find, and you should do the derivative just to make sure everything is fine, what you should find is that you get the minimum spot size when R is equal to L. And what it means is when R is equal to L, this is what we call a confocal resonator. Okay? So these two mirrors are the same, and when the separation here is given by, when R is equal to L, is given by the radius of curvature of these mirrors. So for instance, this mirror has this radius, the center of curvature here, and this mirror has its center of curvature here. So that R, the separation between the two mirrors, is just given by L. So in that case, this is what we call a confocal resonator, and what we found is the spot size is minimum on this mirrors. So what you get is, in fact, a situation like this is you can calculate how big the spot size is on the mirror, and what you see is that the spot size here on the mirror is, well, first you find by taking the derivative that W0 confocal is equal to lambda 0 L over 2 pi n to the power 1/2. And now you find that the spot size on the mirror, for the case of the confocal configuration, is just equal to W0 confocal times square root of 2. So this is where the beam expands by just square root of 2 here on the mirrors. So in the case where R is equal to L, this is when you get the minimum spot size on the mirror. Okay? So this is given by just doing the arithmetic. Okay? So what I'd like to discuss next is the mode stability for a symmetrical mirror cavity. Okay, so let's discuss that case, and I'm going to erase these results here. Okay, so we're going to discuss the mode stability criteria. And we're going to use our previous geometrical optics criteria for mode stability. In the next lecture, I will be able to introduce the concept of mode stability using applied to Gaussian beam. But for now, let's just use the mode stability that were previously found for a resonator or for biperiodic lens system. Okay, so for biperiodic lens system, okay, just before I do that, let me just rewrite the previous expression W12 over W12 confocal. So if you just take the ratio between the two, so for a symmetrical cavity in general divided by W12 confocal, then what we found is this is just the ratio of the two. Is simple, so you get 1 over L over R times 2 minus L over R to the power 1/4. Okay, so now if you plot this as a function of L over R, when L over R is equal to 1 and when L over R is equal to 2, and this is 0, then what you find is, since this is W12 confocal is the minimum, so here the ratio would be equal to 1 at right at this position here, and what we find is minimum like this, and then at L over R is equal to 2, then it blows up here. Okay? It blows up at L over R equal to 0 and at L over R equal to 2. How do we see this? Well, we just look at this expression. We see that when L over R is equal to 0, this expression blows up so that the ratio of these two become infinite. That's what we get here. And here we see that when L over R is equal to 2, then this equation also blow up and we get this situation. So what we see is that the minimum spot size is given by the confocal cavity, and when we get the situation where you get plane parallel mirrors, we get also that the mode size becomes infinite. It means that the light will leak out of the cavity very badly, okay? And we also see that when L over R is equal to 2, in fact this is where L is equal to 2R, which is the concentric situation, then we see also that the spot size on the mirror becomes infinite, which means that we're going to lose the light very badly. So it's become an unstable situation here and there. Okay? When L is equal to 2R, this is the situation here. L is equal to 2R. This is what gives you L over R equal to 2. And this is the concentric cavity. Concentric symmetrical cavity. Symmetrical cavity. And what it means is that you get your two mirror here. It means that the center of this cavity, which is this is R1 and this is R2, then they are concentric. They have the same center here. So it means that the length of the cavity here is L is equal to 2R. Okay? So this is the situation where you get a concentric cavity. The mode size is unstable. And this is that situation, the mode size become infinite on the mirror. Okay? So, but in between, you get a stable situation. Okay, so having derived this, we're going to look to a situation where we go back to our geometrical optics result and see what this geometrical optics result tell us about stability of these different cavities. Okay? Okay, so let's do that. Okay, let's do that. So we're going to use the previous stability condition in geometrical optics. You remember we get in geometrical optics, so we get 0 plus or minus, smaller or equal to 1 minus d over 2f1 times 1 minus d over 2f2, where d is the distance between the lens, and between different lenses, and this has to be smaller or equal to 1. Remember, this was our stability condition in geometrical optics for a biperiodic lens system. Okay, we've seen that two mirrors that form a cavity can be seen also a biperiodic lens system. In the case, what we need to do is we do the substitution d. It was the spacing between the lens. Now we have taken the spacing between the mirror to be L, so we replace d by L, and we replace f1 by r1 over 2, and f2 is equal to r2 over 2. Remember, we need to go back to our definition of radius of curvature. What is positive? Okay, and in this case, in geometrical optics, mirrors like this have the same radius of curvature. In the case of Gaussian beam, this one has a radius of curvature which is positive, and this one has a radius of curvature which is negative, okay, because we're talking of Gaussian beams. We have a slightly different definition of what is positive, what is negative. Now we're going back to our geometrical optics, so we can take F1 to be R1 over 2 and F2 equal R2 over 2, okay, for mirrors of this type, like this, okay, and you can form a cavity. Okay, so now the stability condition becomes, here, if we make that substitution, then we get 1 minus L over R1 times 1 minus L over R2, smaller or equal to 1. Okay? That's our condition for our stability condition. Now, we're going to make a substitution. We're going to call L over R1. We're going to define this as X, capital X, and we're going to define L over R2 as capital Y. Okay, so now we can rewrite this expression as 1 minus capital X times 1 minus capital Y, smaller or equal to 1. Okay, so now we want to find out which region this cavity is stable. So what we can do is we can look when this equation when this equation is equal to 1. So when 1 minus X times 1 minus Y is equal to 1. That's the limiting case here. Okay? So when we do this, then you can write that 1 minus Y is equal to 1 divided by 1 minus X, and this implies that Y is equal to 1 minus 1 over 1 minus X, and putting this on the common denominator, you get 1 minus X in the denominator, and you get 1 minus X minus 1, so you get minus X here over 1 minus X. Okay? So this is our expression here. Y is equal to minus X over 1 minus X. Okay, that would be an upper limit here of stability. And okay, I need to make some room, so I have to erase this, unfortunately. And so we get Y is equal to this. So what we can do is just plot here capital X, capital Y, and we want to plot this curve here. Okay? What we see is that at X equal to 0, then Y is equal to 0. This curve here is going to this point, and then there is interesting point is that when X is equal to 1 and when Y is equal to 1. Okay? Why is the interesting point? When X is equal to when X is equal to 1, here you see that this equation become diverging. Okay? And if X goes to 1 from a value lower than 1, then the denominator will be positive and the numerator will be negative, so it will go to minus infinity. So this curve will go to minus infinity like this. And now when X goes to minus infinity here, then this goes to Y is equal to 1. So when X goes to minus infinity, this converges to Y equal to 1. So this is what the curve looks like. This is what this curve looks like. It looks like this. Okay? That's for one branch. And then we have to look when X is slightly larger than 1. When X is slightly larger than 1, then this quantity, then when X is slightly larger than 1, then the denominator is negative, and then the numerator is negative, so the ratio of the two is positive, so it goes to plus infinity. So you get a curve that goes like this, and then it goes, when x goes to plus infinity, then this goes to plus 1, so like I've shown here. So it approach plus 1, and so you get these two curves. So these two curves here is a plot of this equation here. Okay. Now when this is equal to 0 now, okay, when this is equal to 0, then in that case x is equal to 1 or y is equal to 1. Okay. So you get these other curve that goes like this, and then you get this curve that goes like this, like this. Okay? So now it means that this expression here is telling you that anything in between, like this, and here between these two curves, is stable. Okay? This is between 0 and 1 here. So everything in between these two curves is stable. Okay? So this is the region of stability, the one that I've drawn these bars there are the region of stability. So if you go beyond, the case where smaller or equal to 1, then you would be here, it would be unstable, or it would be high loss, if you like. It would be high loss here. It would be high loss here, high loss here, and unstable and high loss here. It means that the spot size, you would lose the light. Okay, that's what it means. So it's high loss. Okay, but in the region between these two, in the region where there are the lines here, these regions are stable and low loss. Okay, so we can look at the point here when y is equal to 2 and x is equal to 2, is that point here, and okay, so this is the point when x is equal to 2 and y is equal to 2. So when x is equal to 2, and here you get, so you get plus 2 here. So when x is equal to 2, y is equal to 2 from this equation. Okay, and you are at that point. And this is what we have seen is when x is equal to 2 is the case where you get a concentric mirror cavity. Okay, that was our previous situation where where the mode size on the mirror was becoming very, very large, which means that the cavity was becoming very lossy. Okay, so here on that curve here, on that straight line here, what we have is, on that straight line we get R1 is equal to R2. That's this straight line. R1 is equal to R2. If R1 is equal to R2, then here, since x is equal to L over R1, and y is equal to L over R2, when R1 is equal to R2, we get this straight line here with a slope of 1. Okay? And here, when R1 at the position where x is equal to 1 and y is equal to 1, we get the situation where we get symmetrical confocal cavity. So that's the confocal cavity here. This is the concentric cavity, and this point here at x equals 0 and y equal to 0 correspond to plane parallel cavity. So two parallel mirror. So this is two parallel mirror. This is when you get the separation between the mirror is equal to L, and here is when the separation of the two mirrors is equal to 2L, or is equal to 2R, I should say. When the separation between two mirrors is equal to 2R, then this is concentric cavity. So these are the 3 points, and every other point here is stable within these region here. Okay, so that's what we have. I guess this would be a good place to stop, because what I'd like to do is next class would be to discuss cavity, stable cavity, but using the language of Gaussian optics, and so that's what I would like to do in the next class. Here, this is a perfect place to stop. So I hope you're going to be able to watch this lecture before the next class. But next class doesn't, the way I've structured it is next class won't depend very much on what we discussed today. But you need to know what we discussed today in order to do your homework, and of course to understand the later material in the class. So photon lifetime is important, and the way I've introduced it, you should understand it perfectly. So if you have some question, I'm available. Send me email or come and see me during my office hour, or go and see my my grader for this class if you have some question. Okay, so we'll see you next class on tomorrow. Okay, take care. Bye bye.